So this was the one I said I was going to go to. This is page 13, question 7. And I don't know whether any of you had a go at the long division video. It was in the early days of recording. So I thought I'd do this one using the long division method. If you did it another way, using the equating, we should get the same answer. So we are told that this is a factor, so we know that that times that must be that, which is how the equating thing works. So straight away I know that A is going to be, sorry, that should say plus C, shouldn't it? Although I straight away know that C is 1. But we'll pretend we don't know that at the moment. And then you can just quite easily use equating to work out B. But I mean, you may be a bit dubious at the moment. I promise you at the end of the day you probably will be quicker with this method. So how do I turn that into that? I multiply it by z squared. Z squared times 2z is 2z cubed, and z squared times 1 is z squared. We then work out the remainder. This will always be 0. That, take away that, is 2z squared. And because we normally would write the remainder up here, but we can't fit it in, we just bring that down instead. How do I turn that into that? Multiply it by z. Z times 2z is 2z squared. Z times 1 is z. That, take away that, that's take away that. And at this point, the old division equivalent of proof relief washes over me, because I now say, how do I turn that into that? It's a 1. 1 times 2z is 2z, 1 times 1 is 1. No remainder means we've done it right. Now, this was probably an easier one to do using the equating method, but yeah, you'll get used to that when you do the factor theorem, which sort of crops up midway through this year, and then you have to just use a calculator to solve that. So you should have got this. And so today I want to talk about an alternative way of representing imaginary numbers. And it's a graphical way. And if you had a look through those videos that I sent you out in the summer, I put it on class charts in the summer on complex numbers, you will have met it. And in fact, in the video, they do it so beautifully because they do it with sort of like an animation. But the rather sort of dull two-dimensional version of it that I'm going to use is called an Argand diagram. So an Argand diagram is an alternative way of displaying a complex number. Well, actually, you can display any number. So I'm going to display my 3 solutions to this equation on an Argand diagram. So an Argand diagram, rather than having an x-axis and a y-axis, has a real axis and an imaginary axis. RE, real, IM, imaginary. And that's because a complex number is made up of a real part and an imaginary part. And we know that in this case we've got a complex conjugate pair. So how do I display that? Well, if I use that as an example, so it's a half plus root 3 over 2 I. Root 3 over 2, so root 3 is 1.7-ish, so 1.7 divided, so this is bigger than this anyway. So here's how we show it, minus a half plus root 3 over 2 I. We go to minus a half on our real axis, so that would be here. And then we go up to root 3 over 2 on our imaginary axis. And we can either just plot a point. Sometimes we're asked to plot complex numbers as points on an Argand diagram, or we can do it as a vector. And so its complex conjugate pair will be that, going down to minus root 3 over 2. And I could even display this, because this is just minus a half plus no imaginary numbers at all. So that's just there. So what I've done there is displayed the 3 solutions to that cubic equation on an Argand's diagram. Okay, an Argand's diagram is just a graphical representation of complete number. And rather than spend ages going through some really noddy examples, the textbook has got a few examples that you may want to go through. So I would encourage you to look at that, which is just about, it's a little bit like vector geometry. Do you remember with vectors you'd say A equals this and B equals that. What does 2A plus B look like? Well, you can do the same thing with complex numbers. It's easy stuff, which is why, I mean, forgive me, I haven't got time to go through all the easy stuff with you. We'll try and stick to the slightly more complicated stuff. And that way we'll hopefully have a good chance of getting through the syllabus. So just keep losing my minutes there. Just turn to page 19 and question 9.
Is anyone else going to bring it up?
So I thought it might be worth just going through. So this question is in the Argand diagram chapter, almost sort of rerunning what we've just done. We've got a cubic here. We'll assume that this is true. We'll skip that bit. So we're going to use what we're being told there to solve it and then show our 3 solutions on the Argand diagram, just like I've shown the 3 solutions of the previous example on the Argand diagram. The only difference is what we're told here. So in the previous question we just did, we were given a factor, but now we're told that z equals 1.5 is a solution. Now, could anyone suggest what a sensible factor would be to use, therefore? What would be the factor that could give me this as a solution? Go on. Oh man, give me
2z plus 3.
Right, now that's really interesting. Yeah, you're absolutely right. You could say z minus 3 over 2. That would be a perfectly good factor. You know, that's what you get from that. But actually, that's going to be really hard work, isn't it? If instead I recognise that I've got a 2z there, so one of these brackets is going to have a 2z in it, why not do just what Ben suggested? Is that not what he said? That's what he said. Oh, yeah. So go on, see if you can work out what goes here. And you know, you might just go with the equating, or you might be brave and be going for a bit of long division. I had one student in year 13 last year, she persevered with equating all the way through, didn't do long division. So yeah, it is possible, but it's much easier in some situations. I suspect you'd probably find equating easier, but if you had a go at that video, it might be right there.
There we go.
Hello again.
And I know it says use algebra to solve it completely. No, we'll ignore that. We'll use our calculator. When we get the quadratic, we'll use our calculator. Yeah. Yeah, sure. you are doing this, it's always tricky here when you're doing a takeaway and that's negative. Minus 19 minus minus 3 is minus 19 plus 3. So there we go, we've got our three solutions represented on an Argand diagram. I have to say, I have no idea why it's called an Argand diagram, but we are about to introduce another word with an arg in it, so I'm assuming the two are linked. My Greek or Latin didn't go to a posh enough school to know Greek or Latin. Okay, so let's focus on this one here, because it's quite a nice round number, isn't it, as imaginary complex numbers go. So this complex number, which we're representing on an Argand diagram, is 4 plus 2i. We have an alternative way of describing it, much in the same way as we can with vectors. We can instead choose to describe this complex number using its length and the angle it makes with the horizontal. So we have an alternative way of presenting a complex number. We've got this form, and we've got a form which I'm going to call modulus and argument form. We refer to the length as the modulus, and we refer to the angle it makes with the horizontal as the argument. And the textbook tends to use alpha for that angle. So, if we're dealing with this 4 plus 2i complex number, can I get you just to use a bit of Pythagoras and a bit of trigonometry to tell me what the length of it is? We we refer to that as the modulus, and the notation we use is that notation there, which we did come across before in a different context. It also means the positive version of it, but it also in this case means the length. And then the argument is the angle, and we just call that arg z, or whatever the complex number. So just use a little bit of Pythag and a little bit of trigonometry to work out the modulus and argument, sorry my pens are on their way out, of that complex number. Certainly leave the modulus in surd form, unless it's a nice round number, which of course it isn't. And the argument, well, we default to 3 significant figures, don't we? We default to 3 significant figures at A level, unless there are a few examples of situations where we don't. But that's our default level of accuracy. So the modulus is the length of the vector, the argument is the angle it makes with the horizontal. And we'll come in a minute to how we deal therefore with vectors like this one. How do we describe that? And hopefully, you can see how it was a simple Pythagoras calculation, and the calculator does all the surd simplifying for us. And then it was shift tan, because tan is opposite over adjacent, and so we got that. Except that's not how it's done, because with complex numbers, modulus and argument form, we don't use degrees. We use a different way of measuring angles, which you will meet in year 13. In fact, they're doing it at the moment. So this is another one of these situations where in order to teach you further maths, I've got to show you something that you're not going to be using until later on. The other way we can measure angles is to use a measure called radians. Maybe something you've come across before. So I'm very quickly going to go through how radians and degrees are related, but actually in terms of what we need to do here, it's really simple, because it's just a setting on the calculator we flick in order to change it from giving the answer in degrees to giving the answer in radians. And you may now realise why there was a little R sometimes on your calculator rather than a D. A radian is the angle you get if you take a radius and bend it and stretch it around the outside of a circle. So imagine that length stretched around the circle. So that length there is the same as that length there. This angle here is 1 radian, or 1 rad. So yes?
Why is that even a thing?
Well, I mean, degrees are a bit of a pain, aren't they? You know, I mean, we've just demonstrated why they're a bit of a pain. We've got a horrible decimal number that we need to, and there are times when radians are, believe me, are more simple. A lot of the time it is effort, and it's a pain. But a lot of the time, in certain situations, it is easier. And there's also part of me that thinks mathematicians like using them because they're not understood by everyone. It's like another way you can sort of make yourself feel a bit more important if you know. Anyway. My first question to you is: how many radians in a full circle? You know, we know it's 360 degrees, but how many radii would it take to fit around the outside of the circle?
Between 4 and 6. Think about it, it's not equally high diameter. Really, this is not quite, right?
How many is it, Ethan?
2 pi.
It is, yeah. It would take 2 pi radiuses to go all the way around the outside of the circle because, I mean, Rory explained it, that's the diameter, isn't it? And, sorry, that's the circumference, and the diameter is 2 radiuses. So it's 2 pi times the radius would take you all the way around the circle. So what that means is 360 degrees is 2 pi radians. And in fact, very often radians are given in terms of pi. So just humour me. Following a similar pattern, tell me what these sort of key angles would be in terms of pi. So it's R-A-D-I-A-N, radian.
That's the height. That's the magnitude.
Okay, so 180 is just pi radians. 60 we would just write as pi divided by 3. 45 pi divided by 4. 30 pi divided by 6. Very often an angle measured in radians will be given in terms of pi. Not always, sometimes we get a decimal number which we need to round. Now, you won't be surprised to hear that my brain too full of 80s song lyrics, so I just remember this. That's the only one I remember. And then I derive everything else from that. But in terms of argument, what we're dealing with today, this is the crucial fact. Because if we go back to our Argand diagram, this is 0. The argument goes around to 180 degrees in that direction, which is pi radians. So, a complex number that was round here would have an argument of pi. This, therefore, would be an argument of pi over 2. What about a complex number that is below the horizontal? Well, that would have a negative argument. So it would have an argument of minus pi over 2, and confusingly, a complex number in that direction, which of course isn't a complex number, is it? That would just be a negative number, would have an argument of, well, it doesn't matter which one it is, we wouldn't describe a negative number in this form, would we? We'd only use modulus and argument in this form. So that means, for example, that if you do a calculation for a complex number like that, you'll probably end up calculating that angle there. Easier to do so, because that would be tan again. So its argument, so let's say this is complex number z. The argument of z would be pi minus that angle, wouldn't it? Because it's this angle here that we want. If we were in degrees, it would be 180 minus that angle. We're not, we're in radians. Let's just make sure we're okay with getting our calculator into radians. It's a simple switch. Well, I say it's simple. It's nowhere near as simple as it is on the scientific calculator.
Shift setup.
So,
I was messing up this earlier. We've got stuff reading.
so it's if you're in you know the calculation mode, shift setup, and you should find it's there. Gra is gradient, whereby 90 degrees is 100. So it's so that would be up to gradient 100%. You know, so that's yes.
On the diagram, is it pi or is it pi radians?
It is pi radians, but we never write radians. Okay. So if you see an angle measurement,
Yeah.
and it involves pi, you know you're in radians. You know you're in radians. So let's do an example from the book. Yes, sorry. Rob.
So when you've got like an argument on the argument on the graph like that.
Yes.
Is there a specific line you measure the angle from? Does it change depending on?
So, I mean, if we use tan, because you know this will be I don't know -4 plus 2i.
Yeah.
So we'd use 4 and 2 to work out that angle using shift
I
tan.
think with like vectors, do you always do it from the north line? Does it change depending
So,
on that?
Argument is always measured from the horizontal.
Right.
So we've got positive and negative round to. So you can't have an argument of more than pi,
Okay. Right.
or an argument of less than minus pi. Right. So I'm on page 21. Come on. Page 21. Example 5. Yeah. Come on. So here we've got a complex number -4 minus I. See if you can find the modulus and argument. So that's just like we did at the beginning of this bit with Pythagoras and shift tan. But we've got to work in radians, and then we've got to do the whole pi minus or whatever thing. Start with an Argand diagram, though. Start with sketching. And of course, this is -1i, so that's all.
Well done, Ruby.
English teachers making the toilet again. Just like I do with gradient, when I'm working out angles, I never worry about the whole positive negative thing. I just say that's 4 and that's 1, and that's what I'm going to do. It's called Z, so I'm going to the modulus and the argument of Z.
modulus in this context have to do with like the other meaning of modulus?
It's really odd, isn't it? Nothing.
Because I kind of get how it's the same notation as absolute value.
Yeah.
Because it's like, if you've got a normal number, like -4, that's 4 away from the origin, so the absolute value -4 is 4.
Yes, yeah, I suppose. Yeah, I suppose if you are. Yeah. So yes, I mean, if you're describing speed in terms of its horizontal and vertical velocity, then your argument would be the actual speed you're going. I suppose. Yeah, is that? Yeah. I mean, I've always just thought of it as the same notation being used for two different things. I guess you may be right. There is a sort of a link there. I couldn't. Maybe something to Google. Right now, we've got a little bit of fiddling, and I have to say, working out what to type in on my calculator sort of makes my head ache. So here's what I'm going to do. I'm going to chicken out of the negative thing, all right? If this angle here is 0.0449 radians, then this angle here is pi minus that. I know there's a negative involved, but the size of that angle is pi minus that. So I'm just going to do shift pi minus answer. Answer, of course, is hidden on this calculator, bizarrely, which gives me 2.8966. So the argument, because it's below, is going to be minus 2.908966, 2 decimal places. Does that make sense? And I guess I'm going to put radians there because it's not obvious that that's radians because there's no mention of pi. So I'm very happy to accept that in this case the use of radians introduces difficulty. It's not easier. It's not easier. Okay, right. 2 questions I was going to get us to look at before I give you a load to do. Page 21, question 1. No, we won't do that. That's too easy. Question, page 22, question 5.
I'm making numbers from text together. If you got something on the graph, it would be 2.89 positive 7 and minus again. That's 4 minus. Yeah.
Okay. Now, I haven't left myself with anywhere near enough time, but Z1 divided by Z2 is this calculation. And if I want to write that in a more easily to understand form, we dealt with this the other day, all I do is multiply top and bottom by the complex conjugate pair of the denominator, which is a bit like rationalising a surd. So go on, see if you can do that bit. And then it's just asking for the modulus and argument of the answer that you get. Lana, did you manage to get on the... Yeah. Good, excellent. Don't let me make you late. So we get, hopefully you get that, have I done that right? I have. So this is asking for the modulus, so the length. The length. So that's just, so this is that overall, this is Z1 over Z2, isn't it? The length, the Pythagoras, yeah, the hypotenuse. Okay, so on this occasion, it's nice and easy, isn't it? Because the angle we work out is the actual angle we're after, the angle with the horizontal. So we get a modulus of root 26 and an argument which is shift tan of a fifth, which is rounded 0.20. I'm trusting that's the case. And so that is that. This is my suggestion. This is lots of practice of finding modulus and arguments. So skip it if you think you can do it. But that's that. If this has all left you a bit then that's a good question to go through. We finished that one, but you might, if we've rushed it a bit, you might want to finish that one off properly at home. And we'll go through 22, question 4, and make sure you change your calculator back to degrees. Because